Hello, everybody. So this is Suresh. I I used to work at Eightfold, and we were pioneering this Eightfold analytics evaluation. I'll give you a brief about the problem statement. So for those of you who are probably hearing the word Eightfold for the first time, Eightfold is an AI company in people space. So one can literally say that if you have to do a people company like Workdays or all the names that we know in today's world, right? Eightfold is a modern approach for that. So, but many of the Fortune 500 companies today use Eightfold for their careers website. So, if you go to any of this Fortune 500, I mean, most famous ones, right? You type careers dot say xyz.com, the traffic is fronted by Eightfold. What it literally means is we have consumer scale traffic that is coming into our platform, which is coming to us as bunch of facts, right? So XYZ tried logging into the careers page. They tried applying to the page. They tried, looking at the job positions. They were interested in applying. They were not interested in applying. The bunch of this factual information that is continuously coming to our system, and we have to store it. And at the end of the day, what we are really interested at is the analytics around all of this, right? So, how many people came in, how many people applied, how many people dropped, to overall understand the experience of people recruiting and other talent management aspects. I tried giving you one scenario, but there are many, many more scenarios in the people organization that you can imagine of, right? Especially when people are trying to navigate the consumer traffic. So what we had is we were storing all this data in Amazon Redshift. We had a very strong ETL pipeline which is moving all this data to Redshift. And just like everybody else, we model this as star schema, right? We have fact tables and dimension tables, and the fact tables, as I just pointed out, are very, very large because these facts are continuously coming to our system. And the dimension tables are also equally very, very large. The reason for dimension tables being large is, at the end of the day, Itfold is dealing with very complex organizations, right? So they have employee data, people data, and all this applications data that is coming into the system, which is translating to dimension tables, right? So that is a very important factor to consider. So we were offering offline analytics for our end user directly via the Redshift, and the scale was not very high. While the data was very high in terms of volume, the scale was not very high in terms of traffic. But as the company grew, we wanted to unlock more and more use cases. We wanted to, provide in-product analytics. We wanted to provide conversational analytics, where the face of the analytics is completely changed now, right? Where when somebody opens up their front-facing product, we want to start with analytics, just like how LinkedIn is doing in some sense, right? So, but OLTP, as you guys know, probably will not be a good fit for this use case. So we had to piggyback on our OLAP database, which in our case was Redshift. And obviously, Redshift, like many OLAP databases, was not scaled for high QPS reads. It's scaled for it is an OLAP system. It is mainly for the back office use cases. So that's where we started this journey of identifying a right OLAP system, because clearly OLTP cannot solve this problem. We need a columnar store. So we wanted an OLAP database that can solve this problem. So we started our journey evaluating bunch of these options like Druid, Spinos, ClickHouse, and StarRocks of the world, and we tried doing POCs with all of them, and we ended up using StarRocks because we liked the way they thought about it. Uh, Given that we are coming from Redshifts of the world and Databrickses of the world, the we care a lot about joins because we have all these fact tables and dimension tables. So there are many databases which assume that dimension tables are going to be small enough, which is not the case in the real world for us. So we wanted a database that can do very well with joins, is despite the fact that dimension tables are large enough. So that's how our journey with StarRock started. I think Naga, I have my friend here, Naga, who's going to give you a technical overview of how we tuned StarRocks for our needs. I'll be here as well. I'm happy to take any of your technical questions at the end. But for the next few minutes, I'll let Naga cover some of the technical details.
Yeah, thank you, Suresh. Uh, hey, everyone. So, yeah, thank you, Suresh, for that introduction. So, I would like to give an initial introduction of what the Redshift architecture is and how we were using Redshift at Eightfold. And later on, I'll give a brief introduction of how we migrated all our, or we are migrating all our data to StarRocks, and what is our end goal with StarRocks, right? And also any possible future work that we are planning to have on StarRocks before enabling all the use cases that we want here. So similar to StarRocks, so Redshift also has an RA3 architecture. So they started with this RA3 architecture, which is with the storage and compute separation, right, where the data is all stored in Redshift managed storage, which is backed by S3, and all the compute nodes are stateless, right? And there is a single leader node, which is fronting all the queries from the SQL clients, coming in from the SQL client. So whenever a SQL client makes a SQL API call, a SQL query, the leader node receives the query, compiles the query into a binary, sends it to all the compute nodes, where compute nodes get all the data from the S3 and cache it in the local storage of those compute nodes as required, and does all the computation and then send back the results to the leader node, which is then propagated back to the SQL clients. Pretty similar to what all these storage and compute separated databases operate on there. So at Eightfold, this is our ETL platform. As Suresh mentioned, we do have a star schema. So we do have clickstream events flowing in from all the callers, all the clients from the application, where we are using Kinesis Firehose to receive all these clickstream events and send it to the Redshift tables using append only format. So there is no upsert or delete use cases here. It's just append only. Just keep inserting data. And then there are dimension tables where we do have upserts and delete use cases, right? But here the dimension tables at Eightfold are not very small as compared to other use cases usually we find online, right? But here the dimension tables are really, really huge, right? Where we had to do heavy lifting of the ETL. But here the ETL layer is completely developed in-house, right? And using these upsets and deletes semantics that Redshift offers, we ingest all of this data to Redshift. Right. So here from the application and the primary store that we have, we stream in the changelog events, perform the ETL, write it to Redshift. So this is our fact table and the dimension table ETL setup. Uh, when it comes to the read queries and the other operational statistics of using Redshift, it is essentially not cloud agnostic, but we do have use cases where we are growing into other clouds as well. So that was one of our problems. And it also had pretty limited concurrency support, right? So where theoretically they publish a number 50 queries per Redshift cluster, which is not a serverless cluster. This is, I'm talking about a provision cluster with a they do have a concurrency scaling solution where we can spin up an ephemeral compute on the fly up to 10 concurrency scaling clusters, right? So but this by itself had its own limitations, right? And if you look at the diagram here, so there is only a single leader node which is taking care of heavy lifting of dealing with the clients, doing all the terminal logic of all the SQL queries, right, doing all the final aggregations if required on the leader node itself. So there is only a single leader bottleneck here. And within Redshift, we do have the data distribution strategy similar to what StarRocks offers, but it's pretty rigid. They do support only the data distribution, which is the distribution key and the sort key, but the callers cannot specify the number of buckets, or there is also no native partitioning support, right, out of the box. Because of this, what happens is even if we are scaling the number of nodes, number of compute nodes, there is a danger of either one single node doing all the heavy lifting for a given customer, or all the nodes participating in the scan queries where it is polluting all the local cache which is cached on the disks. Either that is happening, but because of this rigid distribution strategy, we were facing a lot of challenges where because the product is inherently multi-tenant in nature, there is a really heavy data skew, right, among all our tenants. So that is another problem that we faced. And the query compilation overhead. So where the leader node is compiling the query from the caller and sending the binary to the compute node. So oftentimes we have noticed that some of the query patterns that we had, where if the users are selecting multiple filters on the UI, the it if a query results in a query compilation, so the latency is much higher. Right, so that's another issue that we have seen. And because of the lack of partitioning, there is a very high denormalization cost in case we need denormalization with respect to our star schema, where if we were to do a data modeling where we create some flat tables or one big table where we are combining multiple dimensions or entity attribute values, those kind of operations, that led to a very high denormalization cost because of the way that the refresh of the materialized view work. Here the semantics of the materialized view refresh. So these are all the list of problems that we have faced. So as Suresh mentioned, we did the POCs with a couple of other database technologies, right? And we stick with StarRocks because essentially it was offering a similar kind of strategy, right, which we were accustomed with Redshift. And essentially the kind of constructs that it offered, even if it is not too many features, but the main thing is having partitioning support and the caller where the clients where we can define the number of buckets for a given table is really powerful. We felt it really powerful, which where we thought that it had the real potential to solve our problems of high data skew, right? So this is our new modeling technique that we did with StarRocks. So we have deployed all our clusters in the shared data architecture, again storage and compute separation here. But here we are using the StarRocks native data format here in order to get as much performance as we can get with this StarRocks native data format. And for the data ingestion logic, so this was really good with us because we did all of the heavy lifting with our current ETL pipeline. So it was mostly the lift and shift where we have changed only the load step of the ETL to write it to StarRocks or ingest our data to StarRocks. So that effort was also made easier with the constructs that StarRocks offered. And the data modeling techniques was we use for the fact tables, we use duplicate key tables because again it is insert only, no upsert or delete use cases. But for our dimension tables, we used primary key tables where we had upsert plus delete, and we did it with broker load construct. And for fact tables, we used insert into plus files where all our data input data from all the streams was from another cloud storage or remote storage in a CSV or Parquet format. And for the optimization, we heavily were reliant on the synchronous materialized views construct that StarRocks offered here. So this diagram was the only change where we had to change the load step in the ETL to write it to StarRocks as well in the shared data architecture, as I explained earlier. So just to give a brief summary here, what how our dimension tables layout changed is because our dimension tables are really huge. We went into exploring the partitioning construct offered by StarRocks here. So here, for example, because we can scale both the FEs and the CN nodes or the compute nodes horizontally. So at least for the dimension tables, we started partitioning all our tables by customer ID, right? Where we were also able to define the specific number of buckets, saying that, hey, for all the customers, for every single partition, just create 3 buckets or 4 buckets, where we were able to uh, 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 because StarRocks internally maintains a tablet to a compute node mapping. When a query comes in, not all the compute nodes will be participating in the scan, or not a single compute node will be participating in the scan. Uh, so essentially we were able to solve our biggest headache with our very large dimension tables by partitioning and distributing the data this way. And for the fact tables, we, because it is append only and it is time based data, the time series related data that we were getting, the click streams, we partitioned the tables on a timestamp basis, which is always incrementing in time here. Yeah, so the improvements and advantages that we saw was, again, the table partitioning we saw was a real powerful construct which opened up other use cases like these denormalizations or any other materialized view constructions, where we were able to carefully align all the partitions so that the refreshes of the materialized view is not all or nothing. We can do partition by partition refreshes, which saved us a lot of compute there, right? The materialized view refreshes or the compaction jobs that were running in order to optimize the tables. So this the amount of compute that was required to do this job in Redshift was way too high, but here it is uh, we can scale linearly as we grow with the number of customers, right? And ability to specify the number of buckets again. So that was the real good thing for us, where we can say that, hey, if I have a 100 node or a 200 node cluster, I can just have subset of nodes work on a particular customer's data whenever the queries come in, right? So that was another great advantage that we got. And for warehouse level isolation that was provided for the read and write and maintenance paths, where we were able to isolate all the traffic, saying that ETL has to go to warehouse 1, the all the UI based queries will be coming to warehouse 2 in the same cluster. So that feature capability we were able to leverage. And for the future work, again, so as we are in the multi-tenant world and we have enterprise customers, obviously we do have high data skew. So even if we are talking about these dimension tables, uh, these three tablets, for example, for customer with very less amount of data might be an overkill, but for these three tablets for a very big customer with a large amount of data might not be enough, right? So in order to do this, I think there are few enhancements that are planned down the line from StarRock. So we got that we were actively looking at all the GitHub requests and everything on StarRocks. So for now, what we are doing is, in order to not have very high metadata memory pressure overhead on the FE nodes, we are trying to manipulate or update the number of tablets per partition. So this is a manual work that is happening today, but we believe that these are all upcoming features from StarRocks, which we are waiting for, right? And yeah, another use case was the ETL pipeline. We used broker load there because we needed multi-table and multi-statement transaction, where we were to insert and delete in multiple tables as a single transaction, but making it available with multi-statement transactions once it is available with just the update and the delete semantics will simplify our ETL pipeline, because the load step had to do an additional read, where we are still optimizing the right path there. And also for the exact count distinct, I think at this point we do have exact count distinct use cases on varchar data types. But at this point, again, this is a physics problem as we understand it. So we are still trying to see if we can have a better way to deal these kind of use cases solved from StarRocks. So these are the list of cases that we want to work on in the future with StarRocks. Yeah, so
That's great. Thank you so much, the view. I want to thank you also for presenting not just the detailed implementation of what you did, but also the story of how you came to StarRocks. I think both halves of a presentation like this are so vital to this project as we move forward and try to get more adoption and awareness as we expand StarRocks. So again, thank you so much for the presentation. I do want to open it up. We've got about 3 minutes left for a question from the audience. I'll go ahead and read it off here. says, is there any cache being enabled in CN nodes in order to improve the performance as this is being utilized shared data architecture?
Yes, we are using that the feature of data cache or the starlet star cache heavily, right? Where all our tables we have enabled this data cache by default, so that all the queries which are reliant on the latest set of data, at least from the fact tables, where not everybody needs all the data all the time. We where in the fact tables maybe the latest year of data for all the customers is what the customers are looking for. So yes, we are reliant on heavily using this data cache or the starlet star cache on the compute nodes.
Great.
I'll give you a different perspective there, right? Just to add on to what Naga said. I think at the end of the day, the performance is only going to come if the data is being read from the EBS volumes. S3 IO, while there's a significant improvement in the latencies of object storages and S3s of the world, it is not still as good as what you read from EBS volumes. So you definitely need a layer of cache, that is the EBS volume, if you want high QPS reads. If you don't have this layer, your reads will suffer.
Thank you so much. We've got a couple of minutes left. Let's try to squeeze another 2 questions in here. Venkata says, was migrating the data from Redshift to StarRocks straightforward?
Yeah, I mean, we had to do data dumping from Redshift to StarRocks in one more using one more level of indirection. It was not completely straightforward, but we were using Redshift additional compute where Redshift also has something like multi-warehouse. They call it data sharing feature, where we were able to unload the data from Redshift and start loading that data into StarRocks. So that was a bigger effort, I would say. But I don't know whether I answered that question.
Yeah, I mean we can do it with some work, right? I mean it's not a multi-month project. It is a multi-week, I mean few weeks project. But we can. I mean StarRocks provides enough bells and whistles to import the data, and Redshift provides enough bells and whistles to
Export
export the
them.
data to an S3 bucket.
Great. Thank you so much. We're into our last minute here. So unfortunately, that's the last question we have time for here. But as always, if you have a question that hasn't gotten answered, please do post it in the StarRocks Slack.